Hello everyone, welcome back. Today we are gonna learn transport analogies. Let us begin with the concept of transport analogies. From the book, we know that momentum, heat and mass transfer process are mathematically similar because all three involve transport across a boundary layer. This slide shows three fundamental expressions. First is momentum transfer, that is half F Re equals LCH by delta. Here, F is the fanning friction factor, which is a dimensionless measure of wall shear stress. Re is the Reynolds number, which is defined as Reynolds number equals fluid density into velocity into characteristic length divided by dynamic viscosity. LCH is the characteristic length and delta is the hydrodynamic boundary layer thickness. This equation tells us that the ratio of characteristic length to the velocity boundary layer thickness depends on the friction factor and Reynolds number. Rearranging this equation gives LCH equals half F Re into delta. So the characteristic length is proportional to the product of friction factor, Reynolds number and velocity boundary layer thickness. Second is heat transfer. H equals K upon delta T and Nu equals HLCH by K, where H is the convective heat transfer coefficient, K is the thermal conductivity of the fluid, delta T is the thermal boundary layer thickness, Nu is the Nusselt number representing ratio of convective heat transfer to the conductive heat transfer. Rearranging them gives LCH equals Nu into delta T. So characteristic length equals Nusselt number times the thermal boundary layer thickness. Third is mass transfer. Kc equals dAb upon delta C and SH equals KCH LCH upon dAb, where Kc is the mass transfer coefficient, dAb is the diffusion coefficient of species A and species B, delta C is the concentration boundary layer thickness, SH is the Sherwood number, ratio of convective mass transfer to diffusive mass transfer. Rearranging them gives LCH equals SH into delta C. Combining all three above equations, LCH equals half F Re into delta equals Nu into delta T equals SH delta C. This is the foundation of transport analogy. All three processes share similar mathematical structure. Rearranging the above relation gives half F delta equals Nu delta T by Re equals SH delta C by Re. Now we introduce Stanton number. What is Stanton number? Stanton number for heat transfer equals convective heat transfer coefficient divided by the product of fluid density, velocity and specific heat. Stanton number for mass transfer equals mass transfer coefficient divided by fluid velocity. The generalized form becomes 1 by 2 F equals STH PR equals STM SC, where PR is the Prandtl number, which equals momentum diffusivity divided by thermal diffusivity, and SC here is Schmidt number, which equals momentum diffusivity divided by mass diffusivity. Now we are going to learn Reynolds analogy. Based on the assumptions, velocity boundary layer thickness equals thermal boundary layer thickness equals concentration boundary layer thickness. And another assumption, Prandtl number equals Schmidt number equals 1. Then F by 2 equals STH equals STM. This is valid mainly for gases. It also separates that properties are evaluated at film temperature. Film temperature equals wall temperature plus free stream temperature divided by 2. This is consistent with the book's guidance on evaluating properties at film temperature. Now we move to turbulent flow. Near a wall, three boundary layers exist. Velocity boundary layer of thickness delta, thermal boundary layer of thickness delta T and concentration boundary layer thickness of delta C. Analogy states delta upon delta T equals Prandtl number to the power 1 by 3 and delta upon delta C equals Schmidt number to the power 1 by 3. Substituting into earlier equation, F by 2 equals Stanton number H PR to the power 2 by 3. This term is called Coldman J factor for heat transfer, written as JH. That means F by 2 equals JH equals STH PR to the power 2 by 3. Similarly, F by 2 equals STM SC to the power 2 by 3. This is called Coleman J factor for mass transfer, written as JM. So F by 2 equals JH equals JM. This works when Prandtl number is greater than equal to 0.6 and less than equal to 60. and Schmidt number greater than equal to 0.6 and less than equal to 3000. Again, property is evaluated at film temperature. If Prandtl number equals 1 and Schmidt number equals 1, it reduces to Reynolds analogy. Now we are going to discuss effect of geometry. Flat plate. Pressure acts perpendicular to the plate, no pressure component in the flow direction. Drag equals viscous shear drag only. So F by 2 equals JH equal to JM. This matches flat plate correlations from the book where friction factor, Nusselt number and Sherwood number follow similar power laws. Pipe flow. Pressure drop is due to viscous shear at wall. For turbulent smooth pipe with Reynolds number greater than 10,000, F by 2 equals JH equals JM. Again consistent with pipe flow correlations in the reference text. Cylinder or sphere. Here the fluid flows around a curved surface. Large pressure difference creates pressure drag in addition to the viscous drag. Therefore, analogy holds only when Nusselt number is much greater than 2 and Sherwood number is much greater than 2. This is consistent with the sphere heat transfer correlations like Rance-Marshall and Whitaker in the book. So, what's the takeaway? Momentum, heat and mass transfer are deeply connected. Reynolds analogy works for ideal gas cases where diffusivities are equal. Chilton-Cohnwell analogy extends it to real turbulent flows using Prandtl and Schmidt corrections. And geometry matters. Flat plates and pipe follow analogy more clearly than cylinders and spheres. That's the beauty of transport phenomena. The process, one mathematical backbone.